Welcome to the next session. Now in this session we discuss chapter 7, that is numerical methods. Now let us see what we discuss in numerical methods, particularly in this session. In the title itself we have numerical methods. That means we go for solving equations. Equations can be of two types generally. They are algebraic and transcendental equations. After that we discuss numerical differentiation and numerical integration. So basically we do three type of things in numerical methods. One is solving algebraic and transcendental equations. Algebraic equation means it's a polynomial expression. Transcendental equation means it's a non-polynomial expression, right? Now particularly when you go to algebraic equations, if I take a polynomial of degree n, it has exactly n roots. Now that is very clear aspects. When I deal with, for example, x square plus 5x plus 6 equal to 0, it has exactly two roots. Those roots can be real or complex, they can be anything. But generally, when you deal with second degree polynomial expression, we have exactly two roots. All the roots can be real roots, all can be complex roots. But one real, one complex cannot be possible for second degree equation, right? So particularly we do three type of things. One is solving equations. Of course, they are not accurate values, they are approximation values. After that, we discuss numerical integration. And then we discuss numerical differentiation. So today, we start with solving algebraic and transcendental equations. Particularly in this session, we focus on Newton-Raphson method, which is more effective. Okay. So let me start with few definitions. First one is algebraic equation. Let us see what is an algebraic equation. Suppose I have an expression like this. P of x equal to a naught plus a1x plus a2x square plus and so on plus an into x power n, where a naught comma a1 comma a2 comma and so on an are real numbers and an is not equal to 0. In that case, this is called an algebraic equation. Another word we can use, that is a polynomial expression. Whenever we have polynomial expression, its important characteristic is its degree. See, expression will be like this: a naught plus a1x plus a2x square plus and so on plus an into x power n. We have powers of x. Here the power of x is 1, x is 2, power of x is 3 and so on n. So powers of x are in increasing order. They can be in decreasing order also. So order is not an important issue. But in this case, we have seen the powers of x are increasing order. And here we have some coefficients a0, a1, a2 and so on an. All these are real numbers. And particularly this constant should not be 0, because this is nothing but the coefficient of highest power of x and it should not be equal to 0. So therefore intentionally when you look at this equation, so the highest power of x is n. Therefore, it is called a polynomial of degree n. Let me tell you a few examples. Suppose I have p of x equal to x square minus 4x plus 4. Another example, p of x equal to, for example, x cube minus 3x square plus 3x minus 11. And example 3, p of x equal to, for example, x power 5, for example, x plus 2. Now this is a polynomial of degree 2. It is a polynomial of degree 3. It is a polynomial of degree 5. Note these points. First we start with definition. Algebraic equation. An equation of the form p of x equal to a naught plus a1x plus a2x square plus and so on plus an x power n. An equation of the form p of x equal to a naught plus a1x plus a2x square plus and so on plus an into x power n is called a polynomial of degree n. Is called a polynomial of degree n, where a naught comma a1 comma a2 and so on an are real numbers, where a naught a1 a2 and so on an are real numbers and an not equal to 0. And an not equal to 0. Write these three examples. First one, P of x equal to x square minus 4x plus 4. Second one, P of x equal to x cube minus 3x square plus 3x minus 11. Third example, P of x equal to x power 5 plus x plus 2. Next definition, transcendental equation. Transcendental equation. Now generally in the mathematics world we have two types of equations, polynomial expressions and non-polynomial expressions. So an equation which is not a polynomial expression or an equation which is not algebraic equation is called a transcendental equation. Let us see examples. Suppose I have e power x plus 2 equal to 0. For example, sin x minus cos x equal to 0. E power x minus 4 equal to 0. Now these are not polynomial expressions. So any expression which is not a polynomial is called a transcendental equation. Write this point. An equation which is not algebraic. An equation which is not algebraic is called a transcendental equation. An equation which is not algebraic is called a transcendental equation. Write these three examples. First one, e power x plus 2 equal to 0. Sin x minus cos x equal to 0. E power x minus 4 equal to 0. Now let us see the basic difference between these equations and those three equations. See, always my target is whenever some equation is given to me or to anyone, so their ultimate task is to find the roots of that equation. Now you can see it has exactly two roots. Here my interest is not to find the roots. Then later we will see to find the roots. At first my intention is how many roots are possible? 2 roots, 3 roots, 5 roots. So that means every polynomial of degree n has exactly n roots. That we call it as fundamental theorem of algebra. So next we state that one theorem that is called fundamental theorem of algebra. So what it states is every polynomial of degree n has exactly n roots. Note this point. Heading fundamental theorem of algebra. Every polynomial of degree n has exactly n roots. Every polynomial of degree n has exactly n roots. Now coming to these algebraic equations and non-algebraic equations, let's see the basic difference. Here we cannot have any assurance about the roots. No guarantee. Even if you have transcendental equation, if it has some roots, those roots can be 1 or infinitely many or finitely many. That depends on example to example. But when you look at algebraic equations, we have a specific rule. What it is? If something is a third degree equation, it has exactly 3 roots. If something is a polynomial of degree 17, it has exactly 17 roots. So we know how many roots will be there for a polynomial expression. So at first count is important. But in this case, there is no assurance about the number of roots. It may have exactly 1 root, or it may have finitely many roots, or it may have infinitely many real roots or complex roots also. That's a different issue. Whether they are real roots or complex roots, basically they are roots. Okay. Later we differentiate how many real roots are there, how many complex roots are there. That depends on some basic properties. But if you have polynomial expression of degree n, it has exactly n roots. So that's why the degree is very, very important characteristic for polynomial expressions. Whereas in case of non-algebraic equations, we don't have any specific feature just like degree. That's why we were unable to know how many roots are there for non-algebraic equations. Okay. Now we discuss how to find roots of algebraic and transcendental equations. Of course, we have particularly 4 methods. The first and foremost important method is Newton-Raphson method. Of course, all these methods are not accurate methods. They may give accurate values or approximation values. Okay. So our task is not to find exact roots, only their approximations. So the next concept is solving algebraic and transcendental equations. This one is solving algebraic and transcendental equations. So we have basically 4 iterative methods. So the first method we discuss in this session is Newton-Raphson method. This is most effective technique. Let us say, suppose I have an equation f of x equal to 0. This can be algebraic equation or this can be a transcendental equation. Now I need to find the root of this equation. So here assume that x0 is an initial approximation. This is initial approximation to the root of f of x equal to 0. Initial approximation to the root of f of x equal to 0. When do you say that a number is root? Suppose if f of alpha is 0. Suppose I have f of alpha equal to 0. For some number alpha, it can be real or complex. Then alpha is a root of an equation f of x equal to 0. Is this point clear? So alpha is some number, it can be real or complex. Whenever f of alpha equal to 0, then this number is called a root of f of x equal to 0. Now here my assumption is x0 is an initial approximation to the root of f of x equal to 0. This is only my guess. Only my guess. Suppose if the equation is this, f of x equal to x square minus 4x plus 4. Now its roots are 2 and 2. So to target these two, I may start with x0 value, for example 1.7. So that depends on user to user. That may vary from user to user. So suppose I may start with 1.7, but I don't know exact root is 2. If this is a simple expression, so I know that its root is 2. But I am starting with 1.7. My journey starts from 1.7. So based on this initial approximation, I will try to find the root in the next iteration. This is actually initial approximation. So they will be supplied, they have to supply this even in the examination also. So initial approximation has to be supplied. After that, we need to start finding root values in the iterations wise. The value of root in the first iteration, value in the second iteration, third iteration, like this. So we have different syntaxes. x1, we call it as value of the root in the first iteration. x2, value of root in second iteration. Like this, we continue up to some condition has to be satisfied. Let us say. So here x0 is my initial approximation to the root of f of x equal to 0. Then step 1 of Newton-Raphson method, we calculate the value of root in first iteration, that is x1, using the formula x1 equal to f of x0 divided by f dash of x0. So this is the value of root. So x1 is x0 minus f of x0 by f dash of x0. This is the value of root in first iteration. So x1 represents value of root in first iteration. So x1 is x0 minus f of x0 divided by f dash of x0. This is first order derivative. So once my x1 is over, I compare current value with the previous value. So if x1 equal to x0 implies Newton-Raphson method, that is NR method converges to x0. So my job is over. So basically in this case, whenever this happens, we call it as this method is convergent. So whenever current value matches with previous value, then we say that NR method is convergent and it converges to repeated value. Otherwise, I go for value of root in second iteration, that is x2. So x2 represents value of root in second iteration and it depends on previous value. So it is x1 minus f of x1 divided by f dash of x1. So this is nothing but value of root in second iteration. So current value must depend on previous value. So once x2 is over, compare x2 with the previous value. If x2 equal to x1, implies NR method is convergent and converges to x2. Otherwise, I go for step 3. So that is nothing but x3, the value of root in third iteration. So this is given by x2 minus f of x2 divided by f dash of x2. See, always current value depends on previous value. Like this we continue up to until it has to satisfy the condition xk plus 1 equal to xk for some k. For some k. And this is called condition for convergence. So this is called condition for convergence. So xk plus 1 is nothing but value of root in k plus 1th iteration. So whenever current value matches with the previous value, my job is over. So even if you continue, you will get same repeated values. Say for example, you take some equation, for example x1 is 1.8. Calculate x1, suppose this is 1.9. Current value is not matching with the previous value, go for next iteration. Suppose this is 1.91. Compare current value with the previous value. It doesn't match with 1.9. So calculate x3. Suppose this is 1.92. It is not matching with the previous value. So calculate x4. Assume that this is 1.92. So at this point, we got repeated equal values. So therefore, even if you calculate x5, you will get same value. You calculate x5, x6, x7, continuously you get 1.92. It's a waste of time. So continuously you will get same values. No improvement in the values. So at that case, you can stop the process. Therefore, x4 is matching with x3. Therefore, we got convergence in fourth iteration and therefore it converges to 1.92. But I am not saying that this 1.9 is exact value of root of that equation. If I start with 1.8, maybe I am getting converges in the fourth iteration and it converges to 1.92. If I start with 1.91, maybe I get converges in the second iteration itself. So that depends on situation to situation. But when you choose always suitable approximation, it always converges. So this is the condition for convergence. Xk plus 1 equal to xk for some k. This is called condition for convergence. So as long as there are no repetition of values, we keep on calculate iteration values x1, x2, x3 and so on like this. So whenever there is a repetition of equal values, then you can stop it. So always do iteration value, compare with previous value. If it matches, stop the process. Otherwise, continue the process until some repetition happens. Otherwise, it is not required. Okay. So therefore, xk plus 1 equal to xk is the condition for convergence. Therefore, the general Newton-Raphson formula in k plus 1 iteration is given by xk plus 1 equal to xk minus f of xk divided by f dash of xk. So this is nothing but the general Newton-Raphson formula in k plus 1th iteration where k values are ranging from 0 onwards. So iteration value starts from 0 onwards. Okay. So this is only initial approximation which will be given in the examination. Based on that you need to find. Okay. So note these points. First one, Newton-Raphson method. Let f of x equal to 0. Let f of x equal to 0 be an equation for which root has to be evaluated. Let f of x equal to 0 be an equation for which root has to be evaluated. For which root has to be evaluated. Let x0 be the initial approximation to the root of f of x equal to 0. Let x0 be the initial approximation to the root of f of x equal to 0. To the root of f of x equal to 0. Step 1. Evaluate the value of root in first iteration. Evaluate the value of root in first iteration using the formula x1 equal to x0 minus f of x0 by f dash of x0. Evaluate the value of root in first iteration using the formula x1 equal to x0 minus f of x0 divided by f dash of x0, where x1 is the value of root in first iteration, where x1 is the value of root in first iteration. So this is step 1. In step 1 we are evaluating this. Next, let us do comparison with the previous value. If x1 equal to x0, if x1 equal to x0 implies NR method is convergent and converges to x1. If x1 equal to x0 implies NR method is convergent and converges to x1. Otherwise, step 2, evaluate the value of root. Step 2, evaluate the value of root in second iteration using the formula x2 equal to x1 minus f of x1 by f dash of x1. Otherwise, step 2, evaluate the value of root in second iteration using the formula x2 equal to x1 minus f of x1 by f dash of x1. If x2 equal to x1 implies NR method is convergent, if x2 equal to x1 implies NR method is convergent and converges to x2 and converges to x2. Otherwise, step 3, evaluate the value of root in third iteration. Evaluate the value of root in third iteration using the formula x3 equal to x2 minus f of x2 by f dash of x2. Evaluate the value of root in third iteration using the formula x3 equal to x2 minus f of x2 by f dash of x2. Like this, the process is repeated. Like this, the process is repeated until xk plus 1 equal to xk for some k. Like this, the process is repeated until xk plus 1 equal to xk for some k. And this is called condition for convergence. And this is called condition for convergence. Therefore, the general Newton-Raphson formula, in k plus 1 iteration is given by the general Newton-Raphson formula in k plus 1 iteration is given by xk plus 1 equal to xk minus f of xk by f dash of xk. Highlight this formula where k equal to 0, 1, 2, 3 and so on. 0, 1, 2, 3 and so on. So hope you understand. Majority of the questions in numerical methods will be based on Newton-Raphson method. When you particularly, if you consider the topic of solving equations, this is the most effective. Majority of the questions will be based on Newton-Raphson methods. Okay. So let me discuss what type of questions will be asked based on Newton-Raphson method. Equation will be given, f of x equal to 0. Initial approximation will be given. So they may ask you the value of root in first iteration, or they may ask you value of root in second iteration, or sometimes they may ask you in which iteration the NR method is convergent. So in that case, you repeat the same process as long as the values will be repeated. Okay. Now this is the most effective method. Suppose if xk plus 1 is not equal to xk, if xk plus 1 is not equal to xk for any k, then Newton-Raphson method is called divergent. So there are two words, one is convergent, another is divergent. If xk plus 1 equal to xk for some k, it is convergent. If xk plus 1 is not equal to xk for any k, that means you continue repetitions, evaluations, so you won't get anywhere repetition of values. Suppose x0 is 1, x1 may be minus 1. 1 minus 1, 1 minus 1. So values may be fluctuated alternatively 1 minus 1, 1 minus 1, 1 minus 1. In that case, even if you continue up to 1000 iteration or 1 crore number of iterations, you won't get repetition values. In that case, it is called divergent. So simply we can call like this. Whenever xk plus 1 is not equal to xk for any k, then NR method is divergent. But if you start with a suitable initial approximation, it always converges. It always converges. That is very 100% true. If you start with a suitable approximation value, you will get converges. Maybe the converges may take a long time, maybe in the 17th iteration or 20th iteration. That may be a different issue, but definitely it will be convergent. But if you go for wrong selection of x0, you won't get convergence, and that will be called as divergent. Note 2 points. First point, if the initial approximation x0 is, if the initial approximation x0 is a suitable approximation, note, if the initial approximation x0 is a suitable approximation, then NR method always converges. Note number 1, if the initial approximation x0 is suitable, then NR method always converges. Always converges. Second point, if xk plus 1 is not equal to xk, if xk plus 1 not equal to xk for any k, if xk plus 1 not equal to xk for any k, then NR method is divergent. If xk plus 1 not equal to xk for any k, then NR method is divergent. Now let us handle a few basics on Newton-Raphson method. So we have basically 3 issues based on Newton-Raphson method. The first one is finding square root of a positive real number. Finding square root of a positive real number or using NR method. This is very, very important. Finding square root of a positive real number or using NR method. So here my real number is R. That means I need to get the value of xk plus 1 in terms of xk. That is called recurrence relation. One of the important model. So let x equal to square root of R. So where R is a number which is greater than 0. I need to find out this. So square on both sides. So this becomes x square equal to R. So implies x square minus R equal to 0. So here square root of R is nothing but x value. So finding square root of R is nothing but solving this equation. So therefore here I call it as f of x equal to x square minus R. So finding square root of R is nothing but finding x value. But this x is nothing but root of this equation. So therefore take f of x equal to x square minus R. So therefore the value of xk plus 1 using NR method is xk minus f of xk divided by f dash of xk. So this is nothing but xk minus f of xk is xk square minus R divided by its derivative. We get 2xk. Therefore in this case we get xk plus 1 equal to, simplify this, we get 2xk square minus xk square plus R divided by 2 times xk. So therefore this is xk square plus R divided by 2xk. Therefore the value of xk plus 1 equal to 1 by 2 into xk plus R divided by xk. So this is the recurrence relation to get the square root of R, a positive real number R, that is xk plus 1 is in terms of xk. This is called recurrence relation. Why it is called recurrence relation is, to get xk plus 1, I should know xk. To get xk plus 2, I should know xk. So current value is always depending on previous value. Such procedures are called recursive procedures, and such equations are called recurrence relation. So note this point, this is very, very important. Now I think this is very clear, simple evaluation. So the next one is, let us find cube root of a positive real number, or instead of square root, this is cube root. So the evaluation will be more or less exactly same, slightly result will be different. So here you can take x equal to cube root of r. Here take x equal to cube root of r, where r is a real number which is greater than 0. So apply cubing on both sides, x cube equal to r. So this implies x cube minus r equal to 0. Therefore, finding this cube root of r is nothing but finding x value, but x is nothing but root of this equation. So I take this function as f of x equal to x cube minus r. So therefore, the value of root in k plus 1 iteration using NR method is xk plus 1 equal to xk minus f of xk divided by f dash of xk. This is xk minus f of xk equal to xk cube minus r divided by 3 into xk square. So this is 3 into xk whole cube minus xk cube plus r divided by 3 into xk square. Therefore, the value of xk plus 1 equal to, this is 2xk cube plus r divided by 3 into xk square. Therefore, the value of xk plus 1 is 1 by 3 into 2xk plus r divided by xk square. So this is the formula of xk plus 1 in terms of xk using NR method. So note this, this is also one of the important, very frequent question. Now the third concept is finding reciprocal of a non-zero real number capital R. Finding reciprocal of a non-zero real number R using NOR method. Reciprocal means 1 by R. That's why R should not be 0. So let us take x equal to 1 by R, where R is not equal to 0. Now let us see, I will try to do this in a similar way. Let us see whether we get xk plus 1 in terms of xk or not. My intention is always to get a recurrence relation, that is xk plus 1 must be in terms of xk. I should not have constant expression for xk. Let us see, here x equal to 1 by r. This implies rx minus 1 equal to 0. So I can take f of x equal to rx minus 1. Now let us solve this equation. Here xk plus 1 equal to xk minus f of xk divided by f dash of xk. Here my f of xk is rx minus 1. So this is xk minus f of xk means r into xk minus 1 divided by its derivative is r. So cross multiply this. This is r into xk minus rxk plus 1 by this is r. This will be cancelled. We get 1 by r. Now basically this is not a recurrence relation. So we didn't get xk plus 1 in terms of xk. In Newton-Raphson method, current value must depend on previous iteration value, right? But here we are getting a constant expression for xk plus 1. So therefore this is a wrong choice for f of x. It's a wrong choice. Got this point? Hope you understand. In Newton-Raphson method, you must always get xk plus 1 in terms of xk. It's a recurrence relation. But here we got constant expression 1 by r for xk plus 1. That's why this rx minus k is a bad choice for f of x. Now let us see. Here x equal to 1 by r. So I can take r equal to 1 by x. Therefore, r minus 1 by x equal to 0. Therefore, I can take f of x equal to r minus 1 by x. Therefore, xk plus 1 equal to xk minus f of xk divided by f dash of xk. So, this is xk minus f of xk is r minus 1 by xk divided by the derivative of this. So, its derivative is 1 by xk square. Now, simplify this expression. So, here xk plus 1 is xk into 1 by xk square. So, this is 1 by xk minus r plus 1 by xk divided by 1 by xk square. So, therefore, xk plus 1 equal to, this is xk square into 2 by xk minus r. Therefore, xk plus 1 equal to, this is 2xk minus r times xk square. So, therefore, this is the expression for xk plus 1 in terms of xk. So, we got xk plus 1 in terms of xk. It's a correct recurrence relation. So, this is the right choice for f of x, but it's a wrong choice for f of x. So, note these points. Starting from this onwards. You do not write this evaluation. If you write, this is not a recurrence relation. Now with this, we have finished method 1, that is Newton-Raphson method. Now we discuss one important theorem that is basic for prerequisite for next two iterative methods, that is bisection and regular falsy methods. So the theorem is intermediate value theorem. This is a prerequisite for next two iterative methods, bisection and regular falsy methods. Suppose we have a function f of x. Assume that this is continuous in closed interval a comma b. Actually, my intention is to find the root of f of x equal to 0. So, my target is to find the root of f of x equal to 0. Suppose assume that f of x is a function which is continuous in closed interval a comma b. That means its graph is continuous. And f of a dot f of b is less than 0. So, when product of two numbers is negative, what does it mean? One must be positive and there must be negative. So, if f of a is positive, then f of a must be negative. If it is negative, then this must be positive. But no value should be equal to 0. See, if f of a is 0, then a is a root of my equation. My job is over. I need not discuss these many points. But here I am saying that f of a dot f of b is less than 0. So, product of two numbers is less than 0 means one must be negative and there is positive. But here I am saying that it is continuous. So, continuous means its graph is continuous. Therefore, the graph can be like this, x-axis, y-axis. So, I am saying that the graph is continuous, one value is negative and there is positive. So, therefore, suppose this is A, for example, this is B. Suppose the graph is like this, for example. So, from A to B, the curve is like this. So, it is in the negative zone, it is in the positive zone. That means f of A is negative, f of B is positive. Or you can have reverse case also. Therefore, the graph is continuous between the boundaries x equal to A and x equal to B, and f of A less than 0, f of B greater than 0. That means it must pass through x-axis at least one time, and that crossing point is called root of this equation. Therefore, whenever f of x is continuous in closed interval a comma b and function takes opposite signs at the endpoints, then the equation f of x equal to 0 has at least one root in open interval a comma b. A is not a root, b is not a root, but because of this continuity and because of this property, the equation f of x equal to 0 has at least one root in open interval a comma b. Note this point. Let f of x be a function. Let f of x be a function which is continuous in closed interval a comma b. Let f of x be a function which is continuous in closed interval a comma b, and f of a dot f of b less than 0, and f of a dot f of b less than 0. Let f of x be a function which is continuous in closed interval a comma b, and f of a dot f of b less than 0. That is f of x has opposite signs. That is f of x has opposite signs at the endpoints a and b. That is f of x has opposite signs at the endpoints a and b. F of x has opposite signs at the endpoints a and b. Then f of x equal to 0 has at least one root in open interval a comma b. Then f of x equal to 0 has at least one root in open interval a comma b. We can have this graphical representation. So continuity means graph is continuous, but it is moving from negative zone to positive zone. That means it has to cross through x-axis at least one time, and that becomes root of that equation. So f of x equal to 0 has at least one root in open interval a comma b. Draw this graph. Thank you so much. The session is over. In the next session, we discuss bisection and regular fallacy methods, and this is the prerequisite for bisection and regular fallacy methods. Thank you.